Well, then she did. She got like a couple thousand hours of and even after that, they wanted to push them, and then this practitioner.
So I'm pulling up Husky CT just for like logistics update. We got calendar, due dates. Oh, discussion post. What? 131. Okay, anyway. So we did all that. Now here's homework 1. Hopefully done with that, or at least like something turned in. Now quiz 1 is for tomorrow. That one was posted yesterday morning, so hopefully you saw update about that, ready to rock. And that was based on what we talked about in class, of like what are things that would help us demonstrate that we understood what we were doing, like give you a chance to try it out on your own. So then next thing coming up is that Friday we want to have like project 1. So I thought today we could start talking about it, Friday answer any lingering questions, and then be done with it, ready for the weekend. Sound good? I mean, that's my plan. There's also the reality of what you're actually doing. Are you on this schedule, or is there other things like leftover questions, concepts, or just blazing ahead? Machete's out. Don't ask questions, just keep going forward. All right, so project 1 is different from projects 2, 3, and 4. This one is supposed to be like your guiding light of like, why are you in this class? What are the things that you think will be important? That changes, at least hopefully it changes if you're learning something throughout the semester. So this is not a proposal as in like, if you don't do what you said you would do, you lose. It's more of, based on my current understanding, this is what I think I can do. And then as that changes, then you update. So module 5 will be an independent kind of research project. It's not a big thesis project. It's a small, similar to how we were thinking about in the quiz 1, what were things that helped us demonstrate our knowledge? Same thing for module 5 project. What's a topic that you're interested in that would demonstrate dynamic modeling kind of knowledge stuff? So that's what we're doing. If you're looking for like, okay, well, what are the things that this could be? There are some module 5 like examples, but also take a look at each of the projects that we're going to work on. Like here, a 4-bar linkage in module 2. Module 3 we'll get into looking at constrained dynamic motion. So here for a pendulum, a lot of times we see pendulum solutions as linearized approximations, but we can solve for nonlinear. And so here's like swinging pendulum. And then last thing is module 4, when we're looking at momentum and energy and angular momentum. We'll look at a yo-yo de-spinning mechanism for that one. And all of those, like they're kind of general projects, but also kind of specific. But you could take that and kind of repurpose it for a different kind of project if you want. or come up with something all brand new. So main things that I would start with for a project is kind of like what are the forces involved? So like generally free body diagram. Do you need to have rigid body motion? Like do you have to consider rotation? Is it all single kind of point mass, like just X, Y? Are there constraints on it? Then we're trying to build something, either a career or a hobby or something that you're interested in. Like if you can get through this class, then now you can understand this in a better way. Yeah.
I don't know if it's like concrete. How long would you want it to be around? You know,
The project? How
the
long?
written version, I guess.
For which project? The final project?
For
Or
project one.
oh, for this?
Yeah.
I mean, it can be as simple as like a note card of like, here's my free body diagram, flip on the back. These are the forces that I'm thinking about. It's, yeah. And then I guess there's some other questions about like how to do apply knowledge. So it's about a page worth of, it's not, again, like we're not doing like big in-depth. It's just a chance for you to say like, this is what I think is important. Yeah. Yeah, and some people go really deep into this. Other people try to stay in their comfort zone of like, this is what I know how to do. I know kinematic equations. Let me apply those somehow. But yeah, try it. It's a goal. I'm waiting. Yeah.
So we're making a free body diagram of something that we expect to be a part of our career, basically.
Yeah. Yeah. So, like, do you have general sort of career goals or aspiration?
Yeah.
What is it? What's the
Submarine research.
submarine research? Yeah, so submarine, like submarine can go, you can go all sorts of places there. There's a whole bunch of like little things that are all system mechanics, like pumps and all sorts of stuff. Or it could go like big picture. What makes sub float, right? What makes sub sink? And this was actually a question that people failed to answer at one point. There was a big transfer of technology from US to Spain, and due to miscommunication, the ballast of the submarine was never big enough to actually lift the submarine up. Like it couldn't float. It could sink, which is half of the job, but the more important half of the job is getting back up. So it was too dense, it was too heavy to ever actually stay afloat. So they had to go back to the drawing. It was a huge mess. This was early 20, or like mid 2010s or something, I think, when I was in like grad school. But yeah, anyway, so we have like, if we think about like submarine, as like base stuff, we have weight, we have buoyancy. Neutral buoyancy means weight is the buoyancy. But as you're coming up, you like blast the ballast out to make like the most buoyant, like get as much air into the system as you can so that you can raise up. Yeah, so you could look at like what is acceleration during, like as you're actually like expelling water out and increasing air. What would be the motion there? That's like one example of just very specific. but kind of going from general idea of like submarines to how does a submarine work to all right, submarine is just a dot, and let me see what forces I can apply there. Cool. One example. Let me check in and we'll see if there's like other examples that might help. This is a time to kind of like, I'm big on reflection for a course. I feel like it's the core part of learning. It's like time to actually think about like, what did I learn? How is this, why is this important? Well, this is that time.
Through the ground. Okay. And since it's an angled ramp, technically the backwards force it's experiencing is like the weight cosine. Okay. That part all makes sense to me. The hard part I was having was finding out the forward force and the if we include like friction resistance force. Okay. Yeah. Because like if I do include it, if I do include traction and then resistance, then I have a new dilemma when I do the second part of the problem. Right? It's the opposite. Exactly. Yeah. Since they're perfectly, since there's no acceleration, it's perfect velocity, right? The free body diagram, I feel like maybe my understanding of it was falling apart because I was trying to figure out where to put the mu times normal force.
So that one's an upper bound. Mm-hmm. So mu times normal force is the max force you can apply. Like if you're on flat ground moving at constant speed, friction force is 0.
Okay.
There is no friction because you're not accelerating. Mm-hmm. Here we are. We need to drive up to overcome gravity. Yeah. And then there's not a static friction opposing motion.
Yeah, I was thinking about like the wheels might be resisting the friction, but then you also use that same friction to pull you uphill.
Yeah.
So I was like, how does that work?
And this might be a question. So like kind of quiz related, but also like dynamics, general like expertise in the subject. Let's start here. So we'll go here, add a new page. So let's say like I'm riding a unicycle. I don't know how to ride one, but let's say that I could magically ride one just because it's one wheel, don't have to worry, all the power, everything, it's all. So my velocity, acceleration is both to the right. The only force that the ground can apply to get me to go forward is friction. If I'm moving at a constant speed, that force of friction is 0. Which is kind of weird to most people. Because what's the formula for friction, force of friction? F equals mu n. And that's like, for the most part, that's what I was taught for a long time. This is not a true statement. This is true in limiting cases. Really what we should say is F is less than or equal to mu n. And that's what we saw like with the sliding box in the homework and stuff. Like the friction was constant, it was mu n, but then we came to a stop and now it's 0. So there was some transition where it went from like a constant to 0. Static friction in particular is an upper, whenever we say that it's mu times n, that's saying like it can't be more than that, but it can definitely be less than that. It can be down. Because there is no static force on anything that's not moving here. There's no friction holding it in place on the table. Does that kind of make sense? and that part's weird. So then there's the very real experience of like, well, if I'm rolling a wheel, there is resistance to that wheel motion. Like when you're riding a bike, you can't accelerate indefinitely. Part of that is drag, but there's another part, like a flat tire is much harder to roll than an inflated tire. That one is a different force with the exact same formula. So if I want to include that, it would be something like a rolling resistance. Rolling resistance is still a mu times n formula, but it's a totally different table lookup because it doesn't have to do with two surfaces. It has to do with the wheel and the surface that it's on. Yeah, so rolling resistance is also a mu rolling resistance times n. And again, if you're a super bike nerd like me, you look up rolling resistance coefficients for different tires and different pressures, but it's not friction, because rubber on asphalt friction is like 1.9 to 1, and that's not how much resistance I have to bike. That would be like insane. You might as well pick up the bike and carry it at that point. But anyway, as you're thinking about like projects and you're like, oh, I know friction's gonna push me, and also the quiz, because we also have like friction there. But yeah, really, this is the key to that like rolling static friction. It's an upper bound, it's not an equal sign. That's why, yeah, as engineers, we get to do the fun stuff, like all the weird details of dynamics. In physics, it's just like, ignore friction, it's always 0. It's like, I can't ignore it, I'm trying to use it here, man. Dreams or goals? You should have dreams and goals. Oh, you have no dreams and goals. Oh, man. Jake, we can talk. Or, sorry, Jacob, we can talk. We'll give you some dreams, some goals, some aspirations. You're a UConn engineer. It's like, we're gonna change the world here. Yeah.
What kind of a bike do you have?
I have 3. I have a gravel bike, road bike, and a mountain.
Okay, what's the road bike?
Road is a Cannondale Synex,
Okay.
an endurance kind of bike. Cool.
So then do you just drive for fun, like with your chains, or
Yeah, every day.
every day?
Every single day. Yeah. Throw it in. Then I have a Trek Stash. It's one of those like 29 3-inch tires. That really catch, especially with weeds and mud around here. Finally get some traction. Oh, okay. Awesome. What's upcoming? Yeah, crap. Nice. Other structures. Okay. Yeah. Which part of Okay, great.
And these chains, that makes it very good.
Fan blades are kind of cool. I think them at roughly the half mass length bend, so there's some stiffness. It's like spring mass bounces that rotates them, and so one of the big things, yeah, one of the big things that is hard to design for. It's like what are the natural frequencies of this thing that's being tested? Changes.
Remember if I didn't ask you questions, what questions did you
Oh, for the actual yeah, well, usually they have like a big
So what's the FL? That's the friction you think it was. For me, like I work on this controlled to control. You city comes CITI, especially like the government. Oh, it definitely officially. That's all. She's a professor. You get everything. I'm really worried about that. I'm really worried. I'm making, I'm having repeatable, that's what I do, and then officers that help them, they're gonna help. Finding out what electric drive must meet dire, safe limits based on life. You don't know what those safe limits are. You do research and figure out how much watt, what am I voltage on the currency. So yeah, right. Dangerous, and how we can keep that. It's like, and then we see oh, that's it. I took the time, dude. Yeah, how can we keep the doctor safe with life? Emergency buoy, close down the restaurant. How can we connect the emergency buoy to one other thing? No, I just need you guys to have one little thing. They usually kind of like doors, infinite way to their final designs. So this is what I want you to really look at. From the 15 kilograms, or 6, I think you're 15 kilograms. So, like, dude, this is really helpful. Like, for the hole, for example, you can see those lines. You can see what they made of the island, how they designed this story, proportions, everything they do. You're trying to really do this. To be fair, bro, the first competition is we did this. Interesting. But this is really easy to know, right? Like a lack of physical quality road design safety is difficult. Like the when you jump in for one fall, actually that's serious. And then they switch to a mechanics detail to get the one that has why not try to use a reach group? You're not even close. So the steering is also I need you to it's gotta come, yeah, it's gotta come up. Okay, do you want to also send me the name? Please send me the name, there's an official name. You have to integrate that. You have to show the integration. And so you do well, it just says show your integration. So you just stop it. Stop it. You have to show your integration. It's such an easy thing. It was from A to B to X to it's so easy. To connect acceleration and position, you have to integral points. Yeah. D is D2 T over D2X. Sticking to commitments that we promised you know, take away your position. Obviously, like fought for it. I said, are you sure we should give it to someone like this? And then it was. I'll take it away, sorry. I told him that there's no reason that should be. I'm gonna give it some match. I'm gonna mention it. You have it for now. So call for it. You already just said this isn't even think about it. The main thing I want you to look at is just wait, in like 2 years, in 2 years where you would be taking my principles and their own it's a great accelerator. Sobering design. That's right.
So we were talking, like, came up a little bit about like something dropping or like what is an impact, and we didn't really talk about it in this module 1, but just as like a module 4 idea, because a few people were just thinking about like the idea of like what happens if you drop something or you land on something, or prosthetics and shoes. So there's this idea of like impact is called an impulse. Impact is impulse, which is some kind of like force applied over time. And so impulse is a change in momentum. So if you're moving at one speed and then you have to stop, there was some change in momentum, so therefore there was some impulse applied. So as you're thinking about like, how do I figure out maybe acceleration, like how fast did this accelerate or how fast did something happen? This is a really great way of describing like quick changes in a system. Same thing with explosions. Explosions are usually impulse. They're related to impulse. So the nice thing there is like if I was moving, let's say there was a box falling 10 meters per second, like it's been in the air for 1 second, it's moving 10 meters per second, it's a 1 kilogram box. So F delta T is 1 kilogram times 10 meter per second. So it's 10 kilogram meters per second. That was like my impulse, or we could call that a Newton second. So if the impact happened really quickly, like the box hit the ground and immediately crushed, like in 0.1 seconds, or maybe it like shattered, then we had 100 newtons of force for 0.1 seconds. If it took a whole second, then we had 10 newtons of force over a 1 second time period. And I'm going to call it like average. And that's a big difference depending on like how long you're assuming this impact takes. So a lot of design of like helmets and things that are like trying to protect your body, seat belts, airbags, like all of that is dealing with like we have a large impulse. This number is very large, and that's not going to change. I can't change the speed and the mass of a car crash, but I can increase the time that it takes for all that impulse, for all that momentum to change. And that's what we can do that way. It came up a couple of times, so I thought, and also kind of as you're thinking about what tools do we have or what are we working on. Other things coming up, clarifying questions. It's writer's block, because I said, do something creative. It's like, wow, but I'm not creative. Anything? Any airplane application? Yeah, all right. So one of the reasons so there was a question about like, could I do a project on airplanes? Like, what would that even look like? And one of the reasons I started doing this project, like I got rid of midterms and finals, because someone had taken the midterm, they had turned in they were doing great in the class, and they seemed like interested in dynamics, and they came up and asked like, hey, professor, do you think dynamics would be okay for like airplane design? I'm like, what? And he's like, yeah, does this fit into, I like this course, but I want to get into like aerospace. Like, do you think this fits into aerospace? And I was like, what? Of course. Like, airplanes, so you need F to A. Like, you need force, you need F equals ma. Like that's the core part of getting things off the ground, is balancing forces, figuring this out. So then I realized like I was only talking about stuff that I was interested in, not what you're like actually here in the class to do, because there's so many different ways that you can apply this. Anyway, so long answer to short question of like, what can you do with airplane design? So there's different ways you can go about it. Similar to like a submarine. Like submarine, you could go in and look at like the propeller. Like what is the propeller doing? Or I mean, and a submarine's like a nuclear powered house as well. So you could also look at like the kitchen sink of a submarine. Like how do they keep the kitchen sink so quiet when they're underwater? But anyway, so airplanes, there's like big system level kind of things. And this one's kind of a cool question of like if you lose power, you can still glide, but you can't glide directly straight. Like so there's got to be some angle where you're like dropping, you're changing that potential energy of dropping into forward kinetic energy, and that's keeping the lift enough to keep you in flight. Is that kind of a weird hand wavy thing to do it? So like if you're a certain height up, like how far can you get with no engine? If the engines turn off, something happens. So I know there's still gravity. I know lift is like 90 degrees to that. And then there would also be like some kind of drag on it. So based on how much drag and how much lift, or the ratio of lift to drag, what angle can I put the plane at to coast at a constant speed? It would end up being like kind of a constant speed. Sorry, what was it? So, like, let's say you turn 90 degrees and point straight at the ground. You will accelerate towards the ground because you're basically free falling at that point. So you'd be going faster and faster and faster. You would have tons of lift because you're moving so fast, because lift is proportional to speed. So the faster you go, the more lift you have. So if you go straight down, you have tons of lift.
So there's like a speed where you can't go faster.
Yeah.
No matter what, you're gonna end up going at a constant speed.
Yeah, you would hit terminal velocity, but
So maybe the better question is like, what angle can get you the farthest?
yeah, what angle gets you the farthest? Yeah. Yeah, because you don't want to be going max speed straight down. You want to go as far as you can get. Yeah. How far can you get? Yeah. So that one's kind of a cool like system level of like when we're thinking about this plane and it has a big coefficient lift, like some number to describe its lift, some number to describe drag. What are the limits of driving this thing? Like how far can we get with no engine? Worst case. And then down to like engine level components. There's like rotating blades inside the engine, and those all vibrate. They have to. So roughly, we can kind of say that the motion is like as you're spinning around and it's bouncing back and forth, there's like from that spinning it'll actually change the frequencies that you're vibrating those parts at, like what the kind of natural frequencies are. So you could kind of model that blade as it has a mass, it's because it bends, it's got some kind of stiffness. So let me look at what happens as I'm rotating this thing, and yeah, what do I care about in that sense? That one's more like a little more system level, like each piece. All sorts of possibilities. Cool. Thanks for asking. Other thoughts, questions? Yeah.
What would the kinetics diagram be for that plane moving? Would it have all of the forces, or would it just be the direction that it's moving?
So we would have these forces. Oh. What happened there? And I didn't draw it great. There we go. Or depending on how, so like one way you could split it up is it's called that intrinsic coordinate system, where you have mass times change in speed along whatever path it's traveling at. Here we're saying it's traveling in a straight line, at least in this one specific example. So it shouldn't have like an arc to it. It shouldn't have centripetal acceleration. So that would be one way to do it. That's just my first instinct, is like use intrinsic coordinates for that. It's also nice if you have like something like roller coaster design, of like how fast can I go around this loop. You can use intrinsic coordinates there too, and say like based on how fast the roller coaster comes in and goes around, we know acceleration on the people is always v squared over r in design. I think normal like roller coaster operation, you can't go above like, I don't know, does anyone know roughly how many G's you can put a normal civilian through? 4 or 5? That sounds high. I feel like it's 1.5. 3? Yeah? All right. I know we're out of time, but what? Coney Island says 12 G's? No. That can't be right. 6 G's? 6 sounds so high. I think it's very short time period though. Yeah. But yeah. Jumping is also probably pretty high. Yeah, that's what I was thinking. It's like,
I think it's over a period of time. You know?
Okay.
Maybe
How
12
much
G's
time?
for like half a second. Yeah. Like, you know.
I can't believe Coney Island is number 1. I mean, this also might be an AI generated. Well, I mean, it says roller coaster, right?
I guess when you pull out of
Maybe they were those launcher ones, maybe.
Yeah.
They
I don't know.
super quick at the start.
And it was built in the early 1900s.
It might just have like one super sharp turn.
That would be my guess. Yeah, that's crazy.
What's the red that's no longer active?
Oh, maybe. That's a good question. 4G is a safe limit. gray out. Riders may, so at 4Gs, inexperienced riders may lose consciousness if you're not ready for it.
How do you be ready for it?
I think training, like you have to be exposed to incremental G-force training days, right? Yeah. Mm-hmm. I don't know. It's cool.